This part of the lab is mostly relative to instrumentation systems. In these types of systems, we usually want a voltage that changes in proportion to the parameter we're measuring. An instrumentation system generally consists of a sensor, which converts what's being measured to some kind of electrically related parameter, and an electrical circuit to convert that parameter to voltage. In this lab, we'll design a circuit that indicates strain. This is a strain gauge. It consists of a thin wire or thin piece of metal foil which connects to these two terminals. When the strain gauge is stretched or bent, the wire or foil will stretch. Stretching or compressing the wire makes it either longer and thinner or shorter and thicker. This causes the electrical resistance of the wire to change, since long, thin wires have higher resistance than short, thick ones. Strain gauges are bonded to a piece of equipment to measure the amount of deflection the equipment is experiencing. Usually, strain gauges are bonded to a structural member in order to measure the amount of deformation that member is experiencing. For our lab, I've glued the strain gauge to this cantilever beam. If I bend the beam tip, the strain gauge deflects and the resistance between the red and the black wires will change. This particular strain gauge has an undeflected resistance of about 119.8 ohms. If I bend the beam up, the resistance goes as low as about 119 ohms, and if I bend the beam down, it goes as high as about 120.3 ohms. We want to use this system to create a voltage that indicates the amount of deflection of the tip of this beam. The voltage should be 0 when the beam is undeflected, and the sign on the voltage should tell us which direction the beam tip is displaced. We've already seen that the resistance doesn't change much over the full range of motion, so we probably aren't going to be able to get much voltage variation out of our device. That's one of the things that makes working with strain gauges kind of tricky, as we'll see while doing this lab. In order to convert this resistance change to a voltage change, we'll use what's called a Wheatstone Bridge. I'll talk about those next. This is a basic Wheatstone Bridge circuit. The circuit has a fixed voltage, V sub S, applied to it across these two terminals. These three resistors are all fixed and they have the same resistance R. This resistance varies. It's R plus some resistance variation, delta R. We want to find the relationship between this voltage, V sub BA, and the resistance change, delta R. This circuit consists of two voltage dividers that are in parallel with each other. The voltage V sub A can then be calculated with the voltage divider formula. V sub A is equal to the total voltage V sub S times this resistance over the sum of these two resistances. Since those resistances are the same, this is just V sub S over 2 and it doesn't change. This side of the circuit is also a voltage divider. So V sub B is equal to V sub S times this resistance over the sum of these two resistances, which turns out to be this. So V sub B increases as delta R increases. From these relationships, we can see that if delta R is 0, V sub A and V sub B are both V sub S over 2, and the voltage difference, V sub BA, is equal to 0. Also, since V sub B increases as delta R increases, the voltage difference, V sub BA, increases as delta R increases. So if we put our strain gauge here for this variable resistance, we can get an output voltage, V sub BA, that changes with the deflection of the strain gauge. This circuit is useful from a conceptual standpoint, but it's difficult to implement without using really expensive precision resistors. In our parts kit, for example, the resistor tolerances are in the order of plus or minus 5%. That means that even if we have resistances with the same nominal values, it's very unlikely that they will have the same actual resistance. Another practical problem is that we would need to match the resistance of these three resistors with the resistance of our undeflected strain gauge. Luckily, there's a pretty easy way to create a circuit that allows a lot of flexibility in what resistors we choose for the Wheatstone Bridge. I'll talk about that circuit next. This circuit doesn't require any of these four resistors to be identical, and it uses a potentiometer to do what's called balancing the bridge circuit. When the circuit's balanced, V sub BA is equal to 0. what we'll do is change the resistance of this pot to force V sub BA to be approximately 0 when the strain gauge is undeflected. I'll use the strain gauge as this resistor down here. Its resistance changes as the strain gauge is deflected. We don't have a very wide range of choices of potentiometers in our parts kit, so I'll choose that next. What I want to avoid with the potentiometer is working at the extreme ends of the range of the possible potentiometer resistances. The resistors R1 and R2 can be chosen somewhat arbitrarily in this circuit, but there are restrictions. This circuit still consists of two voltage dividers in parallel. I'll leave the math for you to do, but the general result is that if V sub BA is going to be 0, the ratio of R2 to R1 plus R2 has to be the same as the ratio of the strain gauge resistance to the sum of the two resistances in the right leg of this circuit. To balance the bridge circuit, I can set the value of the potentiometer resistance by monitoring the voltage V sub BA with a voltmeter while I adjust the pot's resistance. If I use this approach, I don't care what value RADJ actually is. I just change the potentiometer position until the measured voltage is 0 with the strain gauge undeflected. I just need to make a reasonable first guess for the resistances, and then the potentiometer can do the fine-tuning for me. This is my bridge circuit. I'm using a 5 kilo ohm potentiometer here, so I have an available range of resistances of 0 to 5 kilo ohms. Since 0 and 5 kilo ohms are the extreme ends of the range of resistance, I've decided to choose a pot resistance of somewhere in the 1 to 1.5 kilo ohm range. That's about 10 times the nominal strain gauge resistance, which was about 120 ohms. That means that R1 here needs to be about 10 times higher than R2 down here. The strain gauge is connected across these two terminals, and the voltmeter is measuring this voltage VBA. I'm using the analog discovery supplies instrument, the red wire and the black wire, to apply 5 volts across these two Wheatstone Bridge terminals. My cantilever beam is currently undeflected, so I want the measured voltage to be 0 under this condition. It's currently about negative 127 millivolts. I'm using the millivolts setting because the voltages I'm going to be measuring are very small. If I change the set screw position, the voltage changes because I'm changing the resistance in this leg of the bridge. Okay, I've got this set to about negative 3.4 millivolts now. I'm probably not going to be able to get much closer to 0 than that. Now if I deflect the beam down, the voltage changes. And if I deflect the beam up, it also changes, but in the opposite direction. If I want to change the signs relative to upward or downward motion, I can just switch the leads on the DMM. In this lab, we created a really simple strain measurement system. I want to emphasize that this lab is intended to give you a feeling for instrumentation systems, rather than make an actual usable strain measurement. We're ignoring a lot of important details relative to strain measurement in this lab. The goal here is mostly to give you an idea of how electrical circuits are used in instrumentation systems.